Morning, my name is Chase Rauckman. I'm a super senior in engineering mechanics and astronautics, and today we're going to take you to space on an elevator. Not actually, but hopefully by the end of the day, I'll be able to convince you that we can do exactly that. So to achieve that, we're going to cover a few different things today. The first is that I'm going to define what a carbon nanotube is. The second is I'm going to explain how a carbon nanotube might be useful in developing this space elevator that I talked about. The third thing we're going to do is discuss three different ways to synthesize these carbon nanotubes, because right now the method is a little bit ambiguous and imperfect. And then lastly, we'll wrap up and I'll give my recommendation on how I believe carbon nanotubes should be perceived in the future. For starters, what is a carbon nanotube? Well, if you imagine this piece of paper as a sheet of carbon atoms, on a molecular level, a carbon nanotube is just that sheet rolled up into a tube. There's no special chemistry going on, no black magic. It's made of the same things that coal and carbon fiber and even diamond is made out of. It's just structured a little bit differently, a little bit stronger. Now the thing about these carbon nanotubes is that depending on how you roll them up, you're going to get different angles between the atoms, different geometries. That's called chirality. And that chirality sometimes determines exactly what properties we're going to get out of our carbon nanotubes. So what properties exactly are we looking for? Okay, well today we'll be discussing the space elevator, which you see kind of a cartoon mock-up below me here. And that space elevator is made up of four components. Okay, the first one is an anchor that's held to the ground. The second one is a counterweight that is orbiting somewhere in space. The third one is the elevator or climber that actually brings things up. And the fourth one is the tether, which is this extremely long rope that holds everything together. Okay, the tether is what we'll be talking about today. The thing about this tether is it needs to be incredibly strong but incredibly lightweight. The reason it needs to be strong is because it has a lot of forces that it needs to hold up to. And it's got to hold up to these gravitational and centripetal forces being acted on by the planet, but then also environmental factors like hurricanes or tornadoes, just high winds that it needs to hold up. So the thing about if we used aluminum or steel or something like that to make this really long tether, to make it that strong, we'd have to use a lot of the material. So much so that it would actually just buckle under its own weight. Okay, so we need something that has a higher strength to weight ratio. Okay, now Brad Edwards. Brad Edwards is the NASA engineer that was first responsible for proposing this idea to NASA. And he said, all right, we can make this thing out of carbon nanotubes. He said if we did, it would weigh about 26 pounds per mile, which is enough for it to hold its own weight. And it would only cost us, with today's manufacturing processes, about $6 billion. That's a lot of money, sure, but compared to the $1 trillion that we're planning to use to go to Mars, it's kind of insignificant. It's cheap. Why don't we? Okay, so he got some of this information from the Itami Molecular Nanocarbon Project out of Nagoya University in Japan. They were the first ones to discover and kind of work with these carbon nanotubes. And some of their data you can see on this graph pictured next to me. Okay, this graph is comparing the strength to weight ratios of different materials. On the low side, you see aluminum, steel, spider silk, carbon fiber, some of the strongest materials that we know of. And those barely even show up on this graph. Okay, the two big bars here are carbon nanotubes experimental value and carbon nanotubes theoretical value at 50,000 and 70,000 kilonewton meters per kilogram. Okay, now I know these are just big numbers, but to put it in some kind of reference frame, the 70,000 value, if you had a carbon nanotube structure about the size of a pencil, you could kind of hold it, and you could support the weight of several elephants in tension. Okay, that's a lot. That's very, very strong. All right. Now the difference between the carbon nanotube theoretical value and experimental value is that we don't yet have a process to get to that 70,000 kilonewton meters per kilogram. And the reason for that is we don't have a synthesis process yet that can make perfect nanotubes with the correct chirality, like we were talking about previously. So in these next slides, we're going to discuss how that might be possible in the future. Okay, so the first synthesis method that I want to discuss is called carbon arc discharge. Okay, this was a method that was actually developed and patented by NASA, so a lot of this information comes from them. But essentially, what this is, it's kind of like welding, okay? So you've got a material over here, so it's going to be carbon, some sort of carbon material. And material over here, also going to be carbon. One's called the cathode, and one's called the anode, which really just means there's going to be electricity going from one to the other. Okay, so we got these two materials. We put a large arc between them, some large electrical voltage. And then what happens is they kind of react, and underneath it, what we get is carbon nanotubes as a product. This is the very quick and dirty way of doing things. So what we end up with is a lot of carbon nanotubes because you just use bigger materials, and the more electricity you put in between them, the more nanotubes we're going to get. The problem with this method is that it's not very exact. You're going to get carbon nanotubes of different sizes and different chiralities, and also there's going to be a lot of waste material. So when you do stuff like this, you also end up getting a lot of soot and stuff that isn't carbon nanotubes. You actually get about a 30% yield, which means whatever you started with, 30% of that is only going to be carbon nanotubes. The second method I want to talk about is called the chemical vapor deposition. This is actually the most widely used technique to develop carbon nanotubes today. Unlike the arc discharge method, which is kind of a brute force type of thing, this is over time you're kind of growing and you're kind of farming these carbon nanotubes. It's essentially just a chemistry experiment. So what you do is you take something that's called hydrocarbon gas and you inject it into a reaction chamber. And this reaction chamber has some sort of like metal catalyst inside it, and over time, with the right conditions, this gas will happen to grow these carbon nanotubes on top of our catalyst, and we'll get kind of a coating of it. Now what's great about this is as long as we use enough gas and enough catalyst, we can also produce large quantities of our nanotubes. And we have a lot of control over this reaction that we're using, and we can produce large amounts of it. Now the problem of it is that we don't have a lot of control over the products. It ends up creating a lot of different versions of chirality and size tubes. We get a lot of defects. It's similar to me going into my chemistry lab and performing whatever experiment the professor wanted me to do, and at the end of the day I'm probably going to get a product that gives me a passing grade, but not exactly what the professor was looking for. The third and final manufacturing method that we're going to talk about today is called laser ablation. So let's first discuss kind of how it works. So again, we're going to have some carbon target that we're going to shoot at, like graphite or graphene or something like that. And essentially we're going to shine a laser right through it, or right at it. And what's going to happen is that laser is kind of going to deteriorate our carbon target, and it's going to convert it into different products. We're going to get some carbon nanotubes and some byproducts like copper or other things that are involved in it. But the good thing about this is that set up properly, these byproducts are really easy to remove, and it's extremely easy to isolate our pure carbon nanotubes. Okay, now this laser actually has a lot of variables involved in it, with how powerful it is and what wavelength laser we're shooting and how far away it is, what angle it's coming in at. And while I don't have the time to be able to go into each of these variables and explain what each of them do, I recommend looking at the peer-reviewed book, Synthesis and Applications of Carbon Nanotubes and Their Composites by Professor Veena Shidari to help understand how that might work. So while there's a bunch of complicated variables that are kind of difficult to manipulate, and that's a bad thing, it's also kind of a good thing, because depending on how we manipulate these variables, we can actually control and retrieve exactly what carbon nanotube we want. We can get the right chirality and the right size for the application we're looking for. The only problem with this is that the laser is limited on how powerful it can be, because if it's too powerful, it just kind of starts to disintegrate our target and we're left with nothing. But it's a good option if we're looking for extremely pure, exact carbon nanotubes. Now that we've covered a few different manufacturing methods on how to produce carbon nanotubes, I'd like to recommend laser ablation to NASA to continue to develop and research. The reason for this is it gives us the exact product we're looking for, and it gives us the highest potential to reach our 70,000 kilonewton meters per kilogram theoretical value of strength to weight ratio. Because laser ablation is a new process, it's not yet fully developed, and if we can find a way to produce high quantities using this method, I believe we can create the tether for the space elevator using this material. In summary, we've covered what a carbon nanotube is, how it can be used, we've covered a few different manufacturing methods on how it can be produced, and I've given my recommendation to pursue laser ablation so that we could potentially build a tether out of carbon nanotubes to build the first ever space elevator. Thank you for listening to my presentation. On the next page, you'll find my bibliography, and if you have any questions, I'd be happy to take them now. Thanks.